Hello students, continuing lectures on microscopy, we will start with matrix methods used in geometrical optics. Now, before starting the matrix methods, we need to know the sign convention. So there are basically four sign conventions. The first one is that all figures are drawn with incident light from left to right. First convention. The second sign convention is that all distances are measured in the same direction in which the light is traveling. Distance measured in the same direction in which the light is traveling. The third postulate is all distances are measured from the optic center of the lens or from the pole of the refracting or reflecting surface. So distance measured from optical center of the lens or from pole of reflecting or refracting surface. Last convention is the transverse directions are taken as positive when measured upward. So transverse directions are positive when measured upwards, and from the principal axis, and negative when measured without. So upward is positive, this is the principal axis, and downward is negative. These are the four sign conventions that are followed in geometrical optics. So apart from these four sign conventions, there are certain assumptions also made. The assumptions are the aperture of the surface is small, and number two is the object is a point object and lies on the principal axis. Number three is the incident ray from the object strikes the surface at a point very close to the pole, so that the angle of incidence and refraction are very small. Incident ray, it strikes the object at a point very close to the pole. So at angle of incidence and a diffraction very small. And the fourth assumption is the incident ray, the refractive ray, and the normal make small angles with the principal axis. So the incident ray, the refracted ray, and the normal they make small angles with the principal axis. So it's called an oblique incident and oblique refraction. Oblique incident or refraction. Now, in matrix method, we will first start with the following system. We have a lens here, and there is a point P. So it is incident at an angle theta. So from the normal angle theta, and you take this distance as x1, and just before it strikes the surface, let's take this distance as x2. Let's call this one as m and this one as q. The distance between these p and q, let it be d. And let this angle be alpha 1 and this angle be alpha 2. So if we look into, if we take this coordinate x1 alpha 1, this actually it represents the coordinates of the ray at P. Now we introduce something called a direction cosine. We introduce quantity lambda 1. It is equal to mu 1 cos theta, and it is the optical direction cosine of the ray at P. And mu1 is of course the refractive index. So instead of writing x1 y1, you can x1 alpha 1, we will now represent it by lambda 1 x1. So it will represent the coordinate of the ray at P. Now similar to that, we can also represent x2 y2 as the coordinate of the ray x2 alpha 2 at M, and corresponding to that we will also have lambda 2 alpha 2 at M. Now what we can see that since there is no medium involved, the ray traverses from P to M, so the refractive indices of these two cases are same. So if the refractive indices are same, then so the angles are same. First of all, is the angles are same, alpha 1 and alpha 2. We can write here alpha 1 is equal to alpha 2. This is the first condition. Now we can represent x2. This x2 is will be equal to x1 plus d10 alpha 1. So you can see here x2 mean this distance. x2 is equal to x1, this distance, plus this additional distance, which we can call it as d tan alpha 1 or alpha 2, whatever. Let me write this one again. x2 is equal to x1 plus d tan alpha 1. Now since the value of alpha is small, so we can represent tan alpha 1 as simply as alpha 1. So x2 will be equal to x1 plus d alpha 1. Now as lambda 1 is equal to mu1 cos lambda 1, so since for the same reason, since alpha 1 is small, we can write mu1 as equal to mu1 alpha 1 and mu2 as equal to mu2 alpha 2. Alpha 1 is equal to alpha 2 and lambda mu1 is equal to mu2, so lambda 1 is also equal to lambda 2. So in that case we can write this quantity x2 as equal to x1 plus, instead of writing d here, instead of writing alpha 1 here, we can represent the alpha 1 by mu1 by lambda 1 by mu1. So d remains intact, and alpha 1 from this equation is equal to lambda 1 by mu1. So if we consider these two equations, one corresponding to the direction cosine and another corresponding to the position, we can write it in matrix form. We can write that alpha 2x2 is equal to 1 by d by mu1 into 0 1 alpha 1 x1, and this matrix is the translational matrix represented as the translation matrix T. Once again, T is equal to 1 by d by mu1 0 1 is the translation matrix. So it gives the effect of translation through a distance t. Gives the effect of translation to a distance d. So in a homogeneous medium of refractive index, in a homogeneous medium of refractive index E1. And interestingly, the determinant T 1 d by mu1 0 1 is equal to 1. So this represents the translation matrix. We can calculate the refraction matrix in a similar way. So let me write the expression. So for a refraction matrix, is when it is R, it is equal to 1 0 minus P 1, where P is nothing but the power of the refraction, is equal to mu2 minus mu1 by R into X, which is the power of refraction. Now we have the translation matrix, we have the refraction matrix. Now what we will find out here is a system matrix. That means if we can, it's not that only we can have the ray has to both travel through the same medium and also get diffracted when it comes when it's confront a medium of different refractive index. So that is why we require a system matrix for a particular system. Now if we consider so let's write here system matrix. So if we look into a system which is so this is the grease where any sort of refraction will take place, and this is the point of the incident ray. It traverses this distance d1, and the image is found here. So let's call this one as d2, and the positions let's this one as x1, and the ray traverses here, and then it comes here. Let's call it as x2, and the positions corresponding to this point, let's call this one as x dash, and this one, let's call this one as x double dash. So so we can see there are two translations that will take place, one corresponding to this one, let's call it as t1, and this is t2, and there will be one refraction taking place, or maybe let's call it as r. So we can write the equation concerning the matrix as, if this is the direction cosine lambda 2, so the coordinates will be presented by lambda 2 x2, corresponding it will be lambda 1 x1. So lambda 2 x2, where the ray ultimately reaches, is equal to 1 by d2 using considering mu as equal to 1 into 0 1 equal to 1 d2 0 1, and then it undergoes maybe some sort of refraction as well as translation at the center. So let's call this one as B minus A minus D and C. And lastly, there is also the incident ray travels before it reaches the surface. So in that case, it is into again 1 by minus t. So since we are measuring it in the other way around, it will be minus t, opposite to the direction of the flow of light. So this is plus, so that's why d2 is plus and d1 is minus. It's minus d1 into 0 1, and ultimately you will get x1 lambda 1, the place where it started from. So this matrix ultimately if you do the multiplication of this matrix, ultimately comes out to be the following. It is b plus a d1, it is minus a here, and it is b d2 minus d plus a d1 d2 minus c d1, and it is minus a d2 plus c. This is how it will look like. Now for periaxial rays originating from 0, so if the rays are usually parallel to the x-axis or parallel to the axis, so if we assume that, then we can simply write x1 as equal to 0, because there will be no height involved, and similarly there will be also x2 is equal to 0 for periaxial rays. So the equation that we get considering x2 only, so here it is x2 x1 y1 lambda 1 x1, and so y2 x2 is equal to this this matrix into x1 y1, and so from this matrix we can see that x2 is equal to b d2 plus a d1 d2 minus c d1 minus d plus c minus a d2 into x1. So putting x1 and x2 is equal to 0, so as we have seen for periaxial rays, x1 is equal to 0 and x2 is equal to 0 for periaxial rays. So only this part remains. So we have b d2 plus a d1 d2 minus c d1 minus d is equal to 0. So we can actually get the image planes. That means if we look into if we write the system matrix equation once again, considering lambda 1 x1, so it's lambda 2 x2 into b plus a d1 0 second. This is actually for the image plane. You can write lambda 2 x2 is equal to b plus a d1 into 0 0, then C minus A d2 into lambda 1 x1. Now for x2, if we consider x2 is not equal to 0, and then we can write x2 is equal to C minus A into d2 into x1. So basically x2 minus x1 is equal to 1 by C minus d2 A, and this happens to be the magnification, magnification m, the distance obtained after and before the refraction has taken place. So we can write it as equal to 1 by, or rather it's called the 1 by m. Similarly, we can write b plus from the previous equation. That means from this equation we can write b plus a into d1 is equal to 1 by C minus A d2, and it is equal to 1 by m. So we get ultimately the matrix equation as x2 lambda 2 is equal to 1 by m minus a into 0 m into lambda 1 x1. So this is actually the system matrix, where m is the magnification.